All right, friends, let's talk about how gradient descent actually updates our parameters. In the previous lesson, we learned that the goal of the gradient descent is to find the bottom of the valley of what is called the local minimum. Gradient descent is basically your friend whispering in your ear, hey, take a tiny step this way, now a tiny step that way, and eventually you reach the lowest point or the local minimum. That whisper is basically this formula. Let's break down the formula and see what each piece means. W is the parameter we are trying to improve to achieve the lowest possible cost. Alpha, which we also call the learning rate, is how big your steps are. Big alpha means giant leaps, and small alpha means tiny baby steps. Slope of J is the tangent line or derivative of J at point W, which tells you which direction to take your step. It basically tells you which way the hill is tilted. Don't worry, you will know more about this later in the lesson. So that's it. Seriously. Now let's talk about that arrow and how it is implemented in the code. When we implement the arrow in the code, we write it this way. In programming, this means take whatever is on the right side and store it in W. It's not claiming both sides are mathematically equal forever. It is basically replacing the old W with a better version of W. Our model usually has at least two knobs to turn, W and B. Gradient descent updates both like this. The important rule to follow here is to update both at the same time using their old values. This is called a simultaneous update. Why we do this? If you update W first and then use the new W to update B, things get really weird and the algorithm stops behaving like true gradient descent. So our code will look like this. Both changes happen together, like two or many friends in larger models taking steps in sync. So gradient descent is basically check the slope, take a gentle step downhill, update W and B together, repeat until you no longer see any noticeable change in the cost. Let's keep things super simple and forget about multiple parameters for a moment. Imagine we have only one knob to turn, a single parameter called W. Our goal? Make the cost function, or J, as small as possible. We mentioned earlier that the slope tells us which way the hill is tilted. Let us see what this means. Imagine you're standing on the right side of a U-shaped valley. If you draw a tangent line at that point, it leans upwards as you go right, meaning the slope is positive. So this is what happens in the update. Subtracting a positive number means W gets smaller, and on the graph, this means we step left toward the local minimum. Beautiful. Gradient descent just said, hey, the cost goes down if you go left. Let's go that way. The gradient descent continues moving left toward the local minimum until derivative of J approaches zero and there is no more noticeable change in cost. Now, imagine you start on the left side of the valley. Let's see what happens in that case. The tangent line slopes downward as you move right. This basically means that the slope is negative. Let's plug that into the update. We can see that subtracting a negative number is the same as adding a positive number. So W gets bigger, which means we step to the right heading toward the minimum. Gradient descent is basically saying, hey, the hill tilts down toward the right. Move that way. The gradient descent continues moving right toward the local minimum until derivative of j approaches zero and there's no more noticeable change in cost. Now that you have intuition for why gradient descent steps the right way, the next question is how big should each step or alpha be? Think of alpha as the pace of gradient descent. We need to choose it wisely because it significantly influences the overall performance and convergence behavior of gradient descent. It can also make your algorithm fast and efficient or painfully sluggish. Basically, picking alpha too small means slow progress because move of W or convergence toward the local minimum becomes very slow. And picking alpha too big means wild jumps because move toward the local minimum might lead to overshooting the local minimum and ending in a divergence. But then how can we choose the best learning rate? There are many practical methods to find a good learning rate, but two of the most popular are starting with a small value. A good range is between 0.001 and 0.1, and most problems behave well somewhere in this range. The second option is testing several learning rates, for example, 0.001, 0.01, 0.03, 0.3, and 1.0. The best learning rate is the one that gives fast decrease in cost and smooth, stable convergence toward the local minimum. Now that we understand how gradient descent updates our parameters, let's see how to use it for linear regression. The idea is simple. We mentioned this before. Look at the slope of the cost function, take a small step downhill, repeat until we reach the local minimum. Basically, this means that for each training example, we look at the difference between the prediction and the actual value. This tells us how far off we are. Then we multiply that by the input value xi. This tells us how much that input is pushing the error. We do this for all training examples, add them up, and then divide by m, the total number of examples, to get the average effect. In case of B, we followed the exact same logic as W, except that in case of B, we no longer need multiplication by xi, or the input value. So each update will become a formula shown here. That's it. These are the formulas used by gradient descent for linear regression. Gradient descent looks at how far our predictions are from the true values and nudges W and B in the direction that reduces the error. Small steps repeated many times results in lower cost, which in turn results in a better model line. In the next lesson, we will see how we can implement gradient descent for linear regression in Python code. See you in the next lesson.